We'll wait about a minute or two to let a few more people get logged in. All right, so I think we left off talking about oxymercuration, and we're going to talk about that and hydroboration together. So let's go down here to this example here. All right, and then I'll just make a separate page for that. Actually, yeah, let's go ahead and let's do the other examples first, and then we're going to come back because the only new reaction we're learning today is this one, MCPVA, which is a epoxidation reaction, and then this one, and oxymercuration, which we'll talk about in detail. Let's go back to here. What would the product be for this reaction here? And give me the name of it and tell me something about it.
Isn't it halogenation?
Good. It's halogenation. That's right.
It's supposed to be cis. The end
Is it,
product.
is it cis or trans?
Right.
It's actually trans, right? Because the
Yeah.
bromines don't want to be on the same side with one another.
Right.
All right. So the product is going to look like this. Right. And remember, just please don't forget this. Anytime you're doing these addition reactions, the double bond is done. It gets used up. So I'm gonna put one bromine here. I'll put one here. And yeah, that's the end of that, right? So there's a bromine gonna be on this carbon and one on this carbon. Most of the times when you're reacting a double bond, that double bond, both carbons are something's gonna happen to both carbons in the double bond. Right. So in this case, you got a bromine that you added to each side, right? And it's always trans.
Does this one follow the Markov rules? I'm not sure to say it right. But
No, this one doesn't. This doesn't necessarily follow Markov-Nikolsky rule. That's more reserved for like addition of HX
okay.
or addition of, because in this particular case, you're adding the same thing to both sides. Like
Right.
bromine is added to both sides.
Okay.
But in these other instances, you're adding something different to each side. Like one part of that is going to be nucleophilic and one is going to be electrophilic. So let me finish that. Always trans. All right. What about here? What's the name of that reaction? And what's the outcome?
Hydrogenation.
Hydrogenation. Good. Okay. I'll
Gonna
take.
make the it's gonna make alkane.
Mm-hmm. Hydrogenation. And the double bond is going to get destroyed. I hate to use that word, but it's going to react. We're going to add a hydrogen to both sides. And it's syn addition. Right, so syn addition. Okay. Any questions about that? We looked at that on Monday, and some of these reactions should start clicking. It should, the wheel should be turning when you see the reagents. What about the next one, HBr? What if I add HBr to that alkene? What's the product?
This is the one that's cis.
And What else? How do I know where to put BR? And how do I know where to put H?
The BR goes on the most substituted carbon.
Right. So this follows Markovnikov's rule, right? So bromine is here. We also add a hydrogen here. That looks so sloppy. We don't have to show that hydrogen, but I'm gonna put it in anyway. All right. But it's addition of HX. And it follows Markovnikov's rule. All right, so now let's take a look at the hydroboration oxidation. This is a new reaction. All right, so let's take a look at that. All right, so with that hydroboration oxidation, this is, for all intents and purposes, it's addition of water. Right, and we can break that down and say H and OH, and is anti-Markovnikov. So what that means is that the OH is going to add to the least substituted carbon, right? And the hydrogen is going to add to the most substituted carbon. If you watch the video, I gave you an acronym or a mnemonic to remember it, right? BAM. Boron is anti-Markovnikov. So when you see this set of reagents, BH3, and then in the second step, hydrogen peroxide and sodium hydroxide, when you see that, then those are the reagents to do what we call hydroborations. So, and it's also syn addition. So for the product, that's going to look like this, right? Where I add an H to one side, and we're going to go through this in a bit of detail. And OH to the other side. Let me fix that. All right. So if you notice again, the OH is now added to the least substituted carbon. This is important, right? If I need a way to make an alcohol from an alkene, I may not want the alcohol to be on this carbon right here, right? What if I don't want it there? What if I want to put it on the other side? I need a method. And so all these reactions are simply tools in a toolbox, and you pull them out when you need them, right? If I want to make an alcohol and I want to put it here, then I need a method to do that. And one of the ways to do it is to use hydroboration followed by oxidation. All right. The other way to do it is up top that we talked about. We mentioned it yesterday, which is to use Oxymercuration. So this is Markovnikov addition of water, H and OH. So let me make another page, and
In
we're
the
gonna
video,
go ahead.
in the video, did you refer to that reaction as MIM?
Yes.
Okay.
So that I gave a mnemonic or an acronym in the video for this one. Right? It was MIM. Mercury is Markovnikov. and then BAM, boron is anti-Markovnikov. All right. Let me put a page in so we can kind of talk about how these things happen. Stop listening in on my conversation, Bixby. These phones are getting out of hand. I think they're snooping on us. What y'all think? Never mind. Don't say it. We're on YouTube. Might get my page deleted. So both of those reactions fall under the category of conversions of alkenes to alcohols. Right. And so if I have an alkene like this one, and I treat it with mercury acetate, and water, followed by sodium borohydride, NaBH4, then I'm going to get the alcohol here. And then the hydrogen here. Right? That's Markovnikov addition. Everybody agree that this carbon in the double bond is more substituted than this one. That's all we're looking at. When we're talking about reactions of alkenes, all we care about is the alkene that's reacting. So that's going to be the product from that. And this is oxymercuration. The other way to convert that into an alcohol is to do what's called, we just talked about that, hydroboration, followed by oxidation. Right? So that's those reagents. You add BH3, and then in the second step, you add hydrogen peroxide, and sodium hydroxide. In this case, your OH ends up here. All right, so this is anti-Markovnikov. And this is Markovnikov. All right, so it's really important to recognize the reagents. So when you see the mercury right here in mercury acetate, that's a dead giveaway that the reaction is oxymercuration. When you see boron, that's a giveaway that the reaction is hydroboration. All right, questions? Any questions so far?
So when we're studying these, I mean, I know you want us like to know like the products and also like the reactants. Do we like? I guess will you be asking like more details? I guess about the mechanism.
Mechanism. It depends on what the reaction is. For oxymercuration and hydroboration, these are really like detailed mechanisms, right? If you watch the video, then you know that the oxymercuration, we could talk about the mechanisms for both. So let's start with hydroboration because we can use the mechanism to explain why it's anti-Markovnikov, right?
Oh, I'm sorry.
right? So if the first thing that happens in this reaction is you have your boron and your alkene here, right? And the reason why this lines up this way is because of the electronegativity difference between boron and hydrogen. So hydrogen in this case is actually partially negative, and the boron is partially positive, right? So if you look at the alkene itself, which carbon do you think is more likely to be positive if I broke the double bond? We talked about this at the very beginning when we did the addition of HX and why it was more Markovnikov and which carbon was more likely to be a cation. What do you think here? If you look at this carbon, how many? What would be the if I broke the double bond? What type of carbon would that be? Tertiary, secondary, primary,
Tertiary.
tertiary. What about over here? It's primary, isn't it?
Yes.
Right. So which one do you think would be more likely to have a plus charge on it? The trend doesn't change. Tertiary is as a cation, tertiary is the best. Methyl is the worst. So it's tertiary, secondary, primary, methyl. So the reason why the hydride is lined up over the tertiary carbon is because that's more than likely where your plus charge is going to be. Right. So when this happens, this pair of electrons come in here, and then the pi bond is going to attack boron. So this goes through what's called an alkyl borane intermediate. So you got this, and your hydride is here. This is also why you see syn addition.
So why was the hydrogen connected to boron? Why was it partially negative? Like what was
It's because of the dipole, the electronegativity difference between the two. That's a dipole going towards that hydrogen.
okay.
So when you see when it's a borohydride like that, the hydrogen is really like almost like, well, not almost, it's a hydride, so it's H minus and not H plus
Okay.
when it's bonded to boron. Right, so this alkyl borane is really a key intermediate for hydroboration, right? And if you notice, you got two more hydrogens on here, so you can actually add two more alkenes to that. Are y'all following that? Every time I have a BH, I can add that across an alkene. All right, so in reality, I need 3 alkenes for every one BH3 because every BH single bond, I can add that across the alkene.
Could you say that again? You need how many alkenes for one pH?
3. So 3 alkenes, the 3-to-1 ratio of
Okay.
alkene to BH3. And the reason is because once I add it once, I still have 2 hydrides on my boron. Right. So I can actually do that again and again. So eventually I'll come to an intermediate that looks like, let's see, make sure I got that. It looks like this. Right, where these are the 2 carbons. Let me change the highlight. These are the 2 carbons in my double bond right here. And it's the same 2 carbons here, here, and here. So you can actually add 2 more alkenes to that. So they're alkyl borane until you get here.
And that's because of you said the BH3.
Mm-hmm. You can see here if I add 1 alkene, I still have 2 hydrides on boron. So I can take that and bring in another alkene that's going to do the exact same thing, right? Add here and then add here. And I can do the same thing down here, where I can add here and then here like that. So I can add 3 alkenes to that. Are we okay with that? Is that making sense or no?
Yes.
All right. And so then it's this alkyl borane. That's all I'm going to get from that first step, right? When I take BH3 and add it to the alkene, this is all I get. That's why I need the second step, which is the addition of hydrogen peroxide and sodium hydroxide. Right, so this part right here, when I take those 2 and add them together, what I'm going to get is well, let me just show you. So the hydroxide part, the sodium hydroxide is a base, right? And that's going to react with the peroxide, which is H2O2, right? So I'm going to do this. And what I'm doing is activating that, because this peroxy anion is going to attack boron, right? So I'm going to get that plus water plus, and then not plus, and then I'll have a sodium. This is negative, and I have a sodium here as a counter ion. Right, so this intermediate right here is really important, because this is what's going to attack that's where your OH is going to come from, right? Because again, the end goal is to turn that alkene into an alcohol. So I'm going to take that alkyl borane that looks like this. And I'm going to attack it. Like so. So once I attack it, I'm going to have a boron that has a negative charge. Right? And so now I can actually see the formation of one of my alcohols from here, right? So I'm going to take this pair of electrons and push them here, and take this pair and push them on the oxygen, onto the other oxygen. So it's going to leave me with B. That's negative, and like that, plus one of my alcohols. Come on, Russell. Yeah. Like that. So it's this carbon right here where the alcohol ends up, which happens to be, in this case, the least substituted carbon. And that's going to happen 3 times. right? And eventually I'll have 3 alcohols plus BOH3, right? Because you can see from here, right? When I attack that 3 different times with that peroxide, eventually it's going to kick off 3 alcohols. And then the boron is going to end up as BOH, right? Because you got water in here too. So that's where you can do proton transfer from water to protonate that. So it'll be that plus BOH3. And that happens multiple times. So once I get to the alkyl borane, I'm just treating that in the second step with hydrogen peroxide and sodium hydroxide to convert the alkyl groups on there into alcohols. So the peroxide attacks, and then you basically have it's almost like a rearrangement where you shift that sigma bond here to attack oxygen, and then you break the OO bond. That's a really weak bond anyway. The oxygen single bond is weak, so you can attack that with no problem. All right, questions about that, about what just happened?
I'm not understanding the last part after the highlighted boron.
Which part? The whole thing?
Not the whole thing, but
Oh,
the
right here, the rearrangement part.
no, I understand the rearrangement, but after that.
Okay, so when that rearrangement happens, do you see how we would get this?
Yes, from the proton transfer, right?
Mm-hmm. So just think about that getting protonated, right? So if I add in H plus, I'm going to have this,
Okay.
right?
Yeah.
So then I'm going to take that and I'm going to treat that again with OOH minus, right? I'm going to do the exact same thing again to give me another, let me get that out of the way. Right, so that'll give me this intermediate. Right, so the boron is going to be negative. So then this is coming here like that. This is coming like that. So then you're going to end up with another alcohol plus B, O minus, OH. Right, with one alkyl group on it now.
Okay.
And then so that's why I'm saying that 3-to-1 ratio is simply because the boron gave up 3 hydrogens at the very beginning. It's going to have 3 alkyl groups on it. And so I'm also going to need 3 equivalents of peroxide to get those alcohols out. So then that can get protonated. So I end up with this. Like that. Then I do it again. Take another peroxide anion and add to that. And the same thing is going to happen.
Okay.
So that's how I end up with the BOH3. You following that?
Yes.
Mm-hmm. And that's how I end up with 3 alcohols. That's why I put a 3X out here.
Okay.
And it explains why it's anti-Markovnikov. It's the very first step that where the anti-Markovnikov regiochemistry comes from. Because the boron ends up on the least substituted carbon. And it's the boron that gets swapped out with oxygen in the mechanism. Right, and then for oxymercuration, let's look at that real quick. The mechanism for that. It's also a pretty detailed mechanism. Cut that off. And I'll put another page in because I'm gonna have to adjust that so it doesn't get cut off. All right, so if I take that same alkene, right, when I add these two together, right, so this is gonna attack mercury like so. And then I'm also gonna add here, right, like that. So I'm gonna end up with a 3-membered mercurinium ion intermediate. So that's Hg, and this is OAC. Mercury is positive, right? And then I have another, the OAC that got kicked off. Right? Is over here. Right? So from that intermediate, water is going to attack it. That's what the purpose, the role of water is. So when you see the mercury plus water, the water actually attacks that intermediate and pops it open, but it's going to attack here. Right, so I'm going to end up with this. Because this is also all right. So I have that plus water. Well, let me not. I need to show this because that was not plus this. Right, and then from that, the OAC that I lost up top can come in and do proton transfer. So I already have my alcohol right here. All right, that's the end of the first step. And then the second step is just to add in sodium borohydride. All right, and this is a source of H minus. All right, so there's some debate about the mechanism for this part, like how it happens, but the overall goal is to take that hydrogen and replace mercury with that hydrogen, right? So I end up with this as my final product. So that H minus is going to replace mercury. Right, and again, the way that happens with the sodium borohydride is debated. There's some debate on whether or not it's radical or whether or not it's polar. I think it's polar, to be honest with you, because that's the simplest mechanism is just to do a substitution.
So when does I always think of like hydrogen being like positive. So when does it act as like a negative ion?
In the case of if it's bound to an atom that has a lower electronegativity, like boron itself, anytime you see a borane like this, right, that's going to have a dipole that way. There are other instances where this is partially negative and this is partially positive. There are other instances like if you have something like this, aluminum is negative in this case, where the whole molecule is negative, and then you'll have a lithium counter ion or something like that. This compound is what we call LAH, lithium aluminum hydride. So in that case, the hydrogen is going to be partially negative. Also, if you have hydrogen bound to a metal, like a transition metal, let's just say, for instance, like a palladium hydride, then it's going to act as a nucleophile. Bless you.
Okay, so it's not a specific group or anything. It's just
Normally, if you see it bound to a metal, or if you see it bound to a metalloid like boron that has a lower electronegativity, then it's going to be a hydride. Otherwise, it's going to act as a proton. Right, so it's a really specific case. So hydrogen bound to metals or hydrogen bound to metalloids like boron, it'll act as a hydride. That's a great question too, by the way. All right, other questions? All right, let's go back up. We got 6 minutes. So let's go back, and I'm gonna fix all this up before I post it. But let's go back to the reaction wheel. We left off. We got one reaction that we didn't do. I want you to do this one on your own. Right? It just says proposal mechanism for the following reaction. So all you're doing is putting the arrows in. We've seen that reaction before. We know it's Markovnikov addition, and we know that the double bond, the pi bond, is acting as a nucleophile. And you got the product, right? So you just need to go through the steps. The next reaction on the wheel right here is epoxidation. Right? What an epoxide is, which is this part right here, is a cyclic 3-membered ether. All right, so it's a 3-membered ring with the oxygen in it, and that oxygen is bound to carbon, like both carbons in the double bond. So the epoxidation, this is one set of reagents, MCPBA, which is metachloroperbenzoic acid, and then follow that up with a proton source, right? MCPBA, if you watch that video that I sent out to you, it looks like this. So it's a type of peroxide, and it has a chlorine here, right? So this is your oxygen source. Right? That's where your oxygen is going to come from. But the epoxide product itself is going to look like this for this particular instance. Right? So you can see again, it's a 3-membered ring. And it's an ether because both carbons in that ring are bound to the same oxygen. All right, that's one way to do that. Another way would be to use hydrogen peroxide and sodium hydroxide. That'll do epoxidation too. The mechanism is a little bit different, not totally different, but a little bit different. But you can do it, you can still do epoxidation with that as well. You can do it with both MCPBA or hydrogen peroxide and sodium hydroxide. Both of those give you the same outcome. All right. So for Friday, we're going to work through, well, we got another part of this to do. We really can finish the rest of this on Friday. We're just going to hit it hard. So make sure you're looking over those reactions. I think I've sent you every video except for, I think we're going to skip the Simmons-Smith reaction. But I think there's only one more, and that's conversion of alkenes into carbonyls, which is only one reaction that we're going to talk about. There's more than one way to do that, but for the scope of this class, there's only going to be one reaction, and it's ozonolysis. So I'll send that today. Yeah. So we're going to stop here. Enjoy your day off tomorrow. I know I will.